talk about why do we need to choose, if we need to choose one data analytics systems, and we will show how Apache Wayang can actually do this for you. I'm Zoe Kaoudi. I'm an associate professor at IT University, and online you saw Haralampos, or Harry for short. He was at TU Berlin until very recently. Unfortunately, he couldn't be here. He's now in UC Berkeley. You can say hello, Harry. We can see you.
Hi. Welcome, everyone, to the talk.
So we will have a hybrid session today. Okay, so let me start by one fact that I'm sure you're all very familiar with, and you mostly, I believe you agree that one size does not fit all applies to data systems and query execution engines. And to illustrate that, so this is the picture we had 12 years ago of all the data systems that were available. And because one size does not fit all, and there have been really many new systems providing a very specific capability. So last year we ended up with this huge picture of different AI and big data systems. So that's the first fact I want to start with. The second one is that at the same time, we have seen that the complexity of the data analytics that we are doing today is increasing. Before, we had mostly relational data, and we were mostly doing SQL queries. Today, we don't have only relational data, we have text data, we have graphs, we have streaming data, image data, and then we don't do only SQL queries, we're building models, we're doing predictions, we may want to mix some graph analytics together with our relational analytics, and even the last years now we have LLMs as well, so we want to put some prediction there in the mix. So I guess you can imagine how users and developers get overwhelmed. So on one hand, you have this complex analytics that you have to build, and on the other hand, you have a zoo of systems from which you have to choose how to build your analytics. And the solutions that we have come up until today is either building hybrid systems like Hadoop DB, for example, that was combining Hadoop with databases, or other systems like SystemDS that was in IBM that was combining Spark with local Java processing. Or you build scripts to do some ETL or ELT pipelines and extract data from one source so that you can do your analysis in some other system. These solutions, first of all, are not maintainable, especially the first one. So Hadoop now is not used so much, so Hadoop DB is deprecated as well. But as well, they're very costly, so like extracting all the data from one source to put it to another source creates duplicate data and is very costly, and also is not optimal. So a user or a developer may not know exactly what is the right engine for their analytics. So we end up in the same overwhelming situation. So that is the problem we want to address, and that's what I hopefully convinced you up to now. So we have complex analytics, we have a zoo of systems, so which one shall we use? Apache Wayang solves this problem, and in the next few minutes, Harry and myself, I will first introduce Wayang and show you what it offers. And then Harry and I will go into the internals to show you a bit how it works. And we will close the session with where the project came from and where we're heading. So let me start with what Apache Wayang offers. So consider how data analytics are implemented today. So every application is effectively locked in a specific one or two data processing engines. So if you write Spark and your company uses Spark, they are locked in with Spark. If you want to use Flink, you have to rewrite everything. Or if you want to use Spark, but now you want to use Postgres as well, it's still possible, but you need to rewrite your application. So what we're proposing is we have to decouple the applications from the underlying processing engines. And we want to do that by adding a virtualization layer between the two, which is given by a multi-engine analytics framework. And this is, in fact, what Apache Wayang is. So it provides this virtualization layer between the application and the data processing engines. So what do we achieve with this decoupling of applications? So first of all, we achieve engine independence. And what does this mean? So imagine you are building your application and you are still in a testing phase and developing phase, so your data is very small. So what you can do is actually build your application normally, but then you can say to Wayang, okay, please execute it in standalone Java program because it's just a small sample and I don't want to waste resources with Spark, for example. So what you would do in the code is actually, you will write, this is the word count example, you would write a word count job, like in a data flow type, like you do in Spark, where you read the data, maybe you remove some spaces, and then you create this word, one pairs, and you reduce by key and you collect. And because you want to run this in Java, you say, okay, I register Java as my plugin. So that's if you know data flow language, that's fairly easy to do. Now you want to actually put your application in production, and you have for some other reason some huge data set, and Java is not scaling anymore. So you would like your application, in fact, to be executed in Spark. So what you would do with Apache Wayang is you would replace this one line of code saying, no, I want to use Spark. So, and that's very simple. So that's the engine independence that Apache Wayang gives us. The second thing that it gives us is automated engine selection. So now the user, in fact, can say, okay, I don't know where to run it, because I'm no expert, so I register 3 platforms or engines that I have available. Here is Java, Spark, and Flink, and I let the system decide where to execute it. And in our initial benchmarks, we did that. This is, again, the word count example, and we had Java, Spark, and Flink as the engines. And then we varied the dataset size, and with star, we denote, in each case, which platform Wayang chose. And if you look very carefully at the numbers, you will figure out that in fact, Wayang could actually select the optimal platform for this task. So that's the automated engine selection property. Another thing that we can do by decoupling the applications from the underlying frameworks is cross-engine execution or multi-engine execution. I'm using the two terms kind of in a similar way. And you may wonder, okay, why do I want this multi-engine execution? Why do I want multiple engines to run just one pipeline? And I will give you 3 reasons for that. So first of all, you may want to do that because you want to optimize performance. So here I have SGD, stochastic gradient descent, a very popular machine learning algorithm. And we can actually decompose this algorithm in a data flow kind of pipeline with this operator, so parsing the input, sampling some data points, computing the weights, updating the model, and looping back. So what now we can do is actually we send the pre-processing part to Spark, so all the data transformation that needs to be done in the entire dataset, we send it to Spark. But then after we sample few data points, we just need a very simple one-thread Java process that will just compute the gradients, update the model, and get a new sample back. And we have seen that by doing that, we can actually decrease the performance, decrease the runtime by 1 order of magnitude. Here you can see we used entirely Java to run STD or entirely Spark. And this red thing is when using the combination of the two. So that's one reason of why multi-engine execution can benefit us. Another reason is because we may have to use multiple engines. For instance, imagine I want to run again an iterative program like STD, but my data is now stored, this doesn't show very well, but my data is stored in Postgres. I cannot do STD in Postgres, right? So I need to query Postgres, get some data out of it, and then move the computation to Spark. So that was the second case. The third case of why we may want to do multi-engine execution is because our data now is in different systems. So we may have data stored in some databases, and then other data sit in blob files in S3. So then, again, we have to use different systems. And here is an example from TPC8, a very well-known benchmark, where we have a join query of 3 relations. And here, you cannot see very well, but here 2 of the tables, so customers and orders, is stored in Spark, in Postgres, and the line item table is stored in Spark. So what we can do is we join the 2 relations here, and then we ship the intermediate results to Spark to do the second join there. Then the final capability that if you decouple the applications from the underlying platforms in the right way, you can also get extensibility. So then in Wayang, we can have new operators, new platforms with just few lines of code. And that is what we initially designed the system for, because we didn't want to fall back to being deprecated because the engines we're using get deprecated. That concludes the first introductory part. So now the third part is to see how Wayang works, so how it achieves all these nice properties. And I will pass it now to Harry to give some of the internals. So if you can change. Yes.
Great. Can you hear me?
Yes.
Yeah, I guess everything is fine. Welcome to the third part of the talk, also from my side. Unfortunately, I couldn't be there, but yeah, we'll do this online. So let's see how Wayang achieves all this, what Zoe mentioned. So the general idea is that we want to decouple applications from the underlying engines, right? So we want users to be submitting applications in our Scala, Java, Python, or SQL API, and then Wayang should take care of the rest. And this we achieve by offering this engine-agnostic API, which essentially then converts to a Wayang plan. And then Wayang creates this execution-specific or engine-specific plan where it picks where operator is going to run on. High level of Wayang. So Wayang jobs get submitted by the users. They're passed to the query optimizer, which it's this engine-specific plant, and then these plants are passed to the executor, which essentially uses all the different engine-specific executors to run the job. And to see how this works, we're going to go through 4 concepts. So first, we're going to talk about operator model, so how we are this decoupling of applications and engine. Second, we're going to talk cross-engine execution, so how this actually works in practice. We're going to talk about the extensible architecture of Wayang, so in which dimensions one can extend Wayang. And then Zoe is going to take you through the optimizer. Great, let's start with the first part now. So to make this a little bit more concrete, I brought this example setup where we have an orders table in a CSV file and then a customers table in a database, and we want to compute the high value revenue per segment. And on the right hand side, you can see the different platforms that we have. So here, for example, we have Java, Spark, and Postgres. By the way, this is just a subset of the platforms currently supported in Wayang. But we want to execute this analytics job, and we have these available platforms. So what users would write is essentially this part. So the first part Zoe also showed before, where we just register the different platforms, and then we have this high-level API, MapReduce-like API, where users can read the text file, parse it to an object, filter it, and then join it with a table from the database, do some more mapping, and then essentially reducing to compute the final sum. By the way, so here you see that users don't really pick the platform that they want each operator to be executed on. But if we would have expert users, they could actually also specify for each operator where they want to have it executed. But in the general case, Wayang will do that for you. And this is the idea is that we have this abstract user-facing API with commonly known operators from, let's say, the MapReduce paradigm, where we have map, filter, reduce, join, etc., etc. And these get mapped to platform-specific operators. So here we see this simple case. So we have abstract operators on the left-hand side, and on the right-hand side, each maps one-to-one to a platform-specific operator. And to make this more concrete, for example, for Spark, you'd have the map abstract operator. This would map to a Spark map operator, would map to a Spark filter operator, on and so forth. So this is the simple case of the one-to-one mappings. But of course, we can also have more complex mappings. So what we call the one-to-n mappings is when one operator maps to other operators. So here in this example, we have a PageRank operator, which maps to this chain of abstract operators. And then, of course, we can have what we call the M2N mapping. So where we map a chain of operators to, again, another chain of operators. So all in all, about the mappings, they're very flexible, and they allow us to call new operators out of existing ones, but also optimize the workloads. Great. Now let's move to the execution after having seen the operator model. So coming back to this example, first derive we call the platform agnostic plan. So what you see on the right-hand side is just a representation of what users wrote on the left-hand side. You see different operators, and then during optimization, Wayang actually each operator. So he's going to walk you through the optimization. What is here important to see is that all of the operators have a little annotation that defines the platform that Wayang chose for them to be executed. So, for example, we have table and map are annotated with a Postgres annotation. Below, map and filter are annotated with Spark, and then on the right-hand side, join reduce are annotated with the Java platform. And then to execute, Wayang will group all operators with the same annotation and put them into one. Right? So here you see on the top On left, you see the Postgres stage, right? So these are the operators that are within the Postgres stage. Below, you see the operators in the Spark stage. And then on the right-hand side, you see the Java stage. And what we see here, those operators between the different stages are what we call data transfer or conversion operators. And these are the ones that allow us to actually move data between engines, right? So we have the result set to stream operator, which allows us to move data from Postgres to Java. And they actually treat it as simple operators during the optimization. Great. But what I want you to take away here in the execution is that Wayang optimizes the plan, decides which platform every operator is going to run on, and then essentially groups all the different operators with the same annotation into stages, and then it can execute different stages also in parallel. For example, here you see that Postgres could be executed in parallel with the Spark stage before joining them in Java. Great, so this is the overview. Again, now we can move on to the extensibility of Wayang. So as I showed you before, we can extend the abstract operators of Wayang. So for example, one could take the existing abstract operators and add a new operator. So for example, here we have PageRank, and we actually compose PageRank out of existing map, reduce, join. By the way, repeat is an operator that allows you to do iterations. So one way to extend is by adding new operator mappings, right? Second, we can also add different execution operators. So for here, you see the abstract operator reduce, and on the right-hand side, you see the different implementations that we have in Spark. So as maybe some of you know, in Spark, you can write a reduce in many different ways, and you can actually plug them in all in Wayang. So you would have for one abstract operator many different engine-specific operator, which allows then the optimizer to have more choice for picking the optimal plan. But what we see here is that one operator can have multiple platform-specific mappings, right? And then finally, we can also extend Wayang with newts, which is also very interesting. So in Wayang, as you saw, we follow open-close principle, where instead of, let's say, code for adding new functionality, extend it. And this is also what happens when adding new platforms. So when you want to add your platform to Wayang so that users can also leverage it during their analytics jobs, you actually have to add a couple of things. So first, you need to add an executor and execution operator that I showed you before. Then you would need to add the mappings of Wayang's abstract operators to your platform operators. Then to be able to move data between Wayang platforms, currently supported Wayang platforms, and your platform, you would need to add those conversion or data transfer operators. You would also need to add some cost model details, for example, how to get execution profile cost estimates. But Zoe is going to talk more about that during the optimizer. But finally, your platform is exposed to the users, and they can actually just register it with one line of code and exploit it for having faster or more capabilities during their analytics. And this brought me actually end of my part. Thank you for listening, and I think now I'm handing over to Zoe again to walk you through the query optimizer.
Okay, great. Okay, so I will now give you the details of how the query optimizer works, which means how the system chooses the different data systems. So the idea is, as Harry mentioned, the user provides a Wayang plan, which is platform agnostic. So initially, this Wayang plan goes into what we call plan inflation phase. And what does this mean is that for each Wayang operator, we use the mappings that we saw before to get an inflated plan. So now we have the same data flow, the same DAG, but now we have like hypernodes of all the possible implementations that exist in the system. So for example, if the first one is a map operator, we will have the orange one as a Spark map and the green one as a Java map, for example. After we have this inflated plan, so this inflated plan somehow incorporates all possible implementations that we can have. So we pass this inflated plan to a plan enumerator. And there is where we will actually try to find all different combinations of implementations. So first we decompose the plan. So we start with having individual nodes. We get all the alternative implementations of all the nodes. Then we start building back the plan again. So we combine sub-plans. And then, of course, we cannot, if we have very large data flows, we cannot just compute all the combinations. That's very expensive. So we need to prune some suboptimal plans. And then we continue back. We try to build the entire plan and find the most optimal execution plan. For pruning, we have 3 different implementations. So the latent operator pruning means that we prune operators when the 2 endpoints of the operator are on the same platform, then we simply choose the cheapest one. The top K pruning just keeps top K instead of keeping just all the plans and then pruning in the end. And the single platform pruning, when the user enables that pruning, it means that the user wants to run the entire pipeline in one platform. So the optimizer takes that into account. As I hinted, and I guess you imagined, when pruning the plans, we need some cost to know which plan is better than another one. And how we do that, I will try to explain in a very high-level view. So I don't want to scare you with this here, but the idea is that we have a cost per operator. And that's a configuration file based. So there is a configuration file that has the costs of all the operators. And then how is this cost defined? It depends on which resources the operator is using, like CPU, RAM, network, disk, and so on. And then how costly these resources are. So the user doesn't have to care about all this, but what we need is, sorry, I forgot, I have an example here. So in the configuration file, you will find something like this. So the load of the filter operator for the Java platform is the cardinality of the filter, so what goes in the operator times a coefficient, plus b, so that's a linear function. And then, so what the system needs to compute all these costs is the cardinality estimation, which is defined at the Wayang level, because regardless of the execution, the cardinality is the same. And this can be either computed or provided. And also we need the parameters, this A and B, we need to estimate them. And we have a profiling tool to do that and learn automatically these parameters. And this, when we build the plans, we combine these per operator costs to get the sum of all the operators that are involved in the plan. What is important here to know is that, as Harry mentioned, data movement operators are normal operators. So we don't have to treat the cost of moving operators from one platform to the other as a different process. So with this operator model, we can actually also account for moving data from one platform to the other. And also another point I want to make here is that by default, we account for runtime optimization. But as our model is kind of pluggable, one could actually change that relatively easy to account for other metrics like maybe monetary cost or energy efficiency and so on. So that was the cost model, the cost-based optimizer. What I want very quickly to mention here is that we also have an optimization process for how to move data from one platform to the other. So the naive way that one would start with is, okay, I just write everything in a file on disk, and then I have the systems reading from there. As you can imagine, this is not very efficient. Another way would be an end-to-end communication. So whenever I plug a new platform, I connect it with all the other platforms. This also wouldn't scale if we have many platforms available. So they're both inefficient, but in different terms. So what we aimed for was a graph-based representation of how the data can be moved. And I will very briefly tell you how that works. So here you can see a channel conversion graph where the nodes are actually data structures that each data system provides. So for example, in Spark, we have RDD, cast RDD, broadcast. In Java, we have collection, streams, in Postgres relation. And here, the edges is actually a conversion operator. So how I convert from a collection to an RDD. So here is missing the symbol, but it's just for visualization purposes. And some of these structures are shared among the different platforms. So now we have to solve the problem. I have a root. I have an operator in Postgres, and then I want to connect it, for example, in two other operators, one in Flink and one in Spark. So then we solve the problem of finding the minimum path from the root to the targets. And that's, although this is an NP-hard problem, that's possible to do because we don't have so many, the graph is not so large. So that's how we also optimize for data movement in Wayang. So that concludes the part with the core concepts of the system. I now want to end the session by how the system, where the system came from and what's our next steps. So the system, in fact, came from research from like 10 years ago. It was called RIM. It was a prototype. And then after publications and development, 5 years later, we applied for an Apache project. We entered the incubation phase of Apache. And in November 2025, so a few months ago, we graduated as a top-level project. So that's where we are now. We are still a small community. So we are 9 PMC members. We have 18 committers, and so far we have 58 contributors. We are also part of the Google Summer of Code this year, where we offered 2 projects. One is to add more engines, especially for data lake support, like Trino, Presto, BigQuery. So there, when you are in the cloud, you really have the dilemma of, okay, which system shall I use? And the second project is implementing a driver, a JDBC driver, so that external applications like Tableau or other visualization tools can directly connect to the system. And so what's next? One thing we are working is still more in research, but now we're trying to actually contribute it back in the community, is building a machine learning-based optimizer. So now I show you we have all these cost formulas where we have to fine-tune the coefficients. It's not so easy to do. So now we're looking at actually using a machine learning model inside the system that predicts runtime of plans so that we make the optimization not only better, but also easier for users to tune. Then we're looking at wider API support. So Python is quite in an early stage. We are extending our SQL API as well. So we're trying to reach to more users in that way. We have also discussed adding a data frame API on top as more for data science people. Another interesting project we're working on, but is still in like very infancy levels of research, is can we use the system to actually choose the platform that will give us the less energy consumption. And we have some preliminary results. So we used machine learning for that because it was not easy to come up with formulas that just estimate energy. But the results seem very promising so far. And finally, we cannot go anywhere without agents, right? So we're looking on how we can use Wayang to actually optimize agentic pipelines. So now pipelines are somehow hard-coded, so you use LangChain or whatever system to orchestrate different agents, but then you fix the engine that you want to use. So we could use Wayang to actually do that automatically in the pipeline. And there we are also looking at now optimizing not only runtime, right? We are also interested in cost because LLMs are very costly. We're also interested in accuracy because now our pipelines are not deterministic anymore. So that's, again, in a research stage. So back to the question, so why choose one? The answer is you don't have to. So with Wayang, we can actually decouple the applications from the underlying platform, and this enables us to implement a cross-engine optimizer that will do this choice for us. So now users can write a pipeline once, and then they can execute it in different engines. And here you can see on the top is our web page. On the bottom is our GitHub repo. As I said, we're just starting as an independent project. We're small. We're looking to grow our community. So if you're interested in either using or contributing, feel free to contact us. And that's it. Thank you very much.
Okay. So thank you very much, Zoe. And
I can take one question, or
yes,
if we have time.
We have time for one question.
Yeah, thank you for the introduction of the tool. So I'm interested in like errors. How do you handle a stack trace, for example? Like at what level do you stop? And if you go down to the smallest level of the platform that you're abstracting, does it mean that I have to know basically the internals of every query engine that Wayang supports?
Very good question. So the answer is no, you don't have to know the details, and that's the purpose of the system, to abstract away the details. So the errors you will get will be at the Wayang level execution, if you get any errors, if that's your question. So if, for example, you should assume that the system will output a correct job to Spark. Now, if there is a problem with the cluster or there are other issues that are directly concerned with Spark, this we don't handle, so it will be an exception set back to the user.
So I have to go somewhere else to look for what's going on underneath.
If it's an infrastructure error, yes. Yeah.
Okay, thank you.
There was another question.
Oh. Sorry.
Thanks. It's a question about the next step. Maybe it's out of scope, but in the machine learning workflow, I would like to ask, how do you create your training data set?
Yeah, that's a very super good question. So we have done research for that, and we have a training data generator. It's called Dataform, which actually uses machine learning to create the training data. A very hard problem there is your training data need the runtimes of different jobs, and to get these runtimes is very costly. We do have a solution there, but it creates maybe what you would call a noisy training set, where the runtimes, some runtimes may be the actual ones, but some others can be estimates. But that's an open problem. Yeah.
Thank you.
Okay. Thank you very much
Okay.
again.
Thank you.